The question we ended with last time, where did the atoms that formed the solar system come from, has two very distinct answers. Virtually all of the hydrogen and 80% of the helium was formed in the first few minutes of the universe, a time we will explore in a future lecture. All the rest, however, the carbon, nitrogen, and oxygen of life, the gold, silver, and platinum, the neon, the iron, the uranium, were all made by stars. It is important then that we turn our attention to the processes which give this essential richness to the atomic world. And we begin by asking the simple question, what is a star? Now, I must confess, this question would not have occurred to me unbidden. I've lived with the knowledge of what stars are for so long that it seems to me as obvious as asking the question, what is water? Or what is a finger? You know what those are because you've known them all your life. The importance of this question, however, for most people was brought home to me by an incident that occurred a few years ago. I grew up in a small town in southeastern Massachusetts, which I considered a very boring place and ran screaming from it at the age of 17, rarely to visit it again. However, a few years ago, I went to visit my late 80-something father, who by that point had joined an organization consisting mostly of other 80-something men in his town, which was in need of entertainment. And so he asked if I would come and give a lecture on what I did. To this event, he invited my two 80-something maiden aunts, who sat quietly in the back of the room and listened. I was giving a talk on neutron stars, a subject that I'm fascinated with and have spent most of my career studying. And in the course of this talk, I said something to the effect that, well, a star is a ball of gas, and then went on to describe the star. And Sophie and Edith, my two aunts, came up to me, rather wide-eyed, at the end of my lecture and said, "Is that what a star is? A ball of gas?" Now, it again seemed obvious to me that everyone should know what a star was just because I knew what a star was. But of course, it's not obvious at all. What you see as a star is a tiny twinkling spot of light that appears night after night in the sky. It's not obvious what that is, and it's certainly not obvious that it's a ball of gas. Furthermore, my statement was slightly incorrect, as you'll see. To an astrophysicist, a star is, and I quote, "a plasma gravitationally bound, supported by thermal pressure and hydrostatic equilibrium, emitting black-body radiation and powered by nuclear fusion." Obviously, this definition was going to be of little help to Sophie and Edith, and probably isn't much help to you too, although over the course of the lectures, many of those terms have been introduced. Recall, for example, from Lecture 2, that a plasma is the fourth state of matter, in which electrons are largely detached from their nuclei. So atoms as such don't exist, but the constituents of atoms, the electrons and the nuclei, are running around independently of each other. Throughout most of its mass, stars are pure plasmas, consisting only of bare nuclei and free electrons. In the outermost atmosphere of the star, the temperature may be low enough, that is, a mere 5,000 or 10,000 degrees, that the collisions are not quite violent enough to always split an electron that happens to join up with a positive nucleus apart. So some electrons recombine and make what are typically ionized atoms, that is, atoms lacking some of their electrons, but not all of them. With electrons in their orbits around a nucleus, they can make transitions to lower and higher orbits, and in the process give off and absorb light. It is these signatures, again unique to each atom, that reveals the chemical composition of the star, something we would otherwise not know, the rotation rate of the star from the broadening of the spectral lines, the atmospheric structure of the star, the temperature of the star, the magnetic field strength of the star, and the surface gravity of the star, which gives us a clue as to its mass and size. All critical inputs to allow us to construct models of stars. So the presence in the atmosphere of a few ionized atoms is key to our understanding the physics of stars. The presence or absence of radioactive atoms can sometimes be detected in a star and can give us a measure of age, but this is not the primary means we have for dating stars. A plasma, then, gravitationally bound. Recall from Lecture 3 that gravity is one of the four fundamental forces of nature, which here determines a star's structure. Although gravity is, as I said, by far the weakest of the forces, the enormous mass of a star is so great that gravity completely dominates its structure. Stellar masses range from about 8% the mass of our Sun to around 80 times the mass of our Sun. In other words, our Sun is a very typical star right in the middle of the mass range. One solar mass, the mass of our Sun, is 2,000 trillion tons, or about 300,000 times the mass of the Earth. Now, why can't we have stars, if they're just balls of plasma, of any size? Why is the limit at 8% the mass of the Sun and 80 times the mass of the Sun? For two different reasons. To power a star, as we'll see, we have to squeeze the core to such a high pressure and density that the nuclei of hydrogen atoms, protons, can stick together and make helium. At 8% the mass of the Sun, a star can just barely generate the pressure and temperature necessary for this reaction to occur. At 7% the mass of the Sun, there's just simply not enough overlying material. The gravitational force is simply too weak to make this process occur. And so, since a star is by definition one that is burning nuclear fuel, less than 8% of a solar mass isn't by definition a star. The upper end, 80 times the mass of the star, is because too much energy, rather than not enough, is being generated. If we go today to a star of 100 or 200 times the mass of the Sun, the energy generated in its core is so great that it will simply blow the star to pieces. And so a stable star can't exist. Thus we have this range of a factor of 1,000 from 8% the mass of the Sun to 80 times the mass of the Sun that encompasses all of the hundreds of billions of stars in our galaxy. Since the strength of gravity depends only on the distance between the two attracting particles, stars become spherical, with some slight distortions if they're rotating very rapidly, where they bulge out at the center, or if they have a companion which raises tides on the star, the way the moon raises tides on Earth. So a star is a plasma that's gravitationally bound. The next part of the definition says that it's supported by thermal pressure. What do I mean by that? Also recall from Lecture 3 that heat is simply the energy of the motion of individual particles. And thermal pressure is the force exerted by those particles as they collide with each other and try to get away, that is, expand from the center of the star. The average speed of a particle, you will recall, is proportional to the square root of its temperature divided by the particle's mass. More massive particles move slowly, higher temperatures make particles move faster. When your tires on your car, for example, get hot in the summer, they expand. Well, what does hot mean? Hot means the air molecules inside your tire are moving around faster, meaning they both collide with the tire walls more frequently, and each collision is more energetic. As a consequence, the pressure of this gas expands the tire. Likewise, the pressure of all the subatomic particles moving around in the stellar core are pushing outward on the material, while gravity tries to bring it in. The surface temperatures of stars range from about 3,000 degrees for those lowest mass stars, only 8% the mass of the Sun, to over 50,000 degrees at the upper end. All temperatures, of course, are on this Kelvin, or absolute physical scale, where 0 represents no motion. So 3,000 to 50,000 degrees. That's on the surface of the stars. But to make particles go fast enough to fuse, as we'll see they need to do, the central temperatures of stars are much higher, ranging from 15 million degrees, as in a star such as the Sun, to over 1 billion degrees Kelvin. So, a plasma gravitationally bound, supported by thermal pressure. All that begins to make sense. In hydrostatic equilibrium, or at least usually so. What do I mean by that? Hydrostatic equilibrium represents the balance between the two forces acting in the star. Gravity, which is always trying to crush the star. Every particle with mass always attracts every other particle with mass, and they always want to get closer together. So gravity, which starts out making a star from a cloud of gas, shrinks it down and wants to keep shrinking all the way to the center. But when it gets hot enough inside, when the particles are running around fast enough, the thermal pressure they exert pushes outwards. Most stars, more than 90% of stars, and our Sun is an example, are in a dynamic balance between these two forces. Gravity that's trying to crush the star and thermal pressure which is trying to expand it. And so, every morning when you get up, the sun in the sky is exactly the same size because these two forces are in balance. And they've been in balance for 4.5 billion years, which is why the conditions on Earth have remained roughly constant over that time, allowing life to evolve. The high central temperatures in the star help in supporting this huge burden of overlying gas. To understand how stars work, we construct models on computers that mean to represent how the star behaves. We do this in a sequential fashion. We start with the outer layer of the star, which we can see directly. We therefore know its temperature very precisely. We know the density of atoms there, and therefore the total mass in the thin shell on the outside of the star, the part we directly observe. We then calculate what temperature and pressure, and therefore density of material, must exist in the thin layer right under the surface to support that surface. If the pressure is too high, the temperature is too high because the atoms are running around too fast, or the density is too high, there's too many atoms pushing out, then the outer layer of the star will lift off in our computer model. That's no good. If the pressure is too low, that is, there aren't enough particles there, the density is too low, or the temperature is too low so the particles aren't moving fast enough, then the outer layer of the star in our model will collapse. And that's not good. And so we adjust the layer one step down from the outside of the star to support the layer above it. Well, now we're on our way, because we've got the outer layer and the next layer below it consistent with that. Now what supports that layer? Well, of course, the layer below that. And so we make the next layer, calculating the temperature, pressure, and density such that it supports layer number 2. And then to layer number 4, supporting layer number 3, etc., all the way to the core of the star. We have a test of this, which I'll describe at the end, which allows us to confirm this model building process. Throughout more than 90% of their lives, stars maintain this delicate equilibrium between pressure pushing out and gravity pushing in. When things get out of balance, however, the star must either expand if the pressure inside is too great, or contract if the pressure inside is not great enough. We'll talk about those processes next time because both are critical in the lives of the stars and the creation of the elements. So, a plasma gravitationally bound, supported by thermal pressure in hydrostatic equilibrium. Emitting blackbody radiation. That's a mouthful. What do we mean there? We see the stars because they radiate light energy into space. Recall from lecture 4, you see how all those early lectures were preparation to what we're building up to here, that moving charges radiate electromagnetic radiation. Positive and negative charges zipping around each other as they are inside a star and on the surface of a star give off waves of electromagnetic radiation, the stuff that we see we call light. The wavelength or color of the radiation given off is related to the energy of the emitting particles. The faster they're zipping around, the higher the frequency or shorter the wavelength of the radiation, and in the case of our eyes, the bluer the color. The slower they're moving, the longer the wavelength. We learned, of course, that the wavelengths that we see are a tiny fraction, only 2% of all the waves possible from radiating charges. The sun has a surface temperature of about 5,800 degrees, meaning that the maximum of its radiation is a wavelength in the yellow-green part of the spectrum. Cooler stars, which means their atmospheric molecules are moving more slowly, are redder, and hotter stars are bluer. If you're very acute and you're in a very dark place, you can actually see a slight tinge to the color of the stars. Some of them are bluer, and some of them are redder. The stars at the head and foot of Orion, the constellation one can see in the winter sky, are a good example of this. The range of energies of the radiating particles leads to a range of wavelengths of the light. As you recall, particles are not moving all exactly the same speed at some temperature. The average speed is given by the square root of temperature over mass, but there's a whole range of speeds. And when we talked about the Earth's atmosphere, we saw that the fastest ones escaped. Well, likewise, in a star, there are fast particles and slow particles, all consistent with a given temperature. And since the fast ones radiate short wavelengths of light, and the slow ones radiate long wavelengths of light, we get a distribution of wavelengths, a distribution of colors. And that distribution has a very particular form related directly to the particular distribution of the radiating particles. and we call that a blackbody spectrum, a spectrum of different wavelengths distributed in a certain way. In the case of our sun, the temperature, 5,800 degrees, defines the peak of that spectrum as being in the yellow-green part of the spectrum. Now, it's not an accident that our eyes are most sensitive to yellow and green light. We have, over 400 million years of evolution, evolved a device, the thing we call our eyes, that's tuned very precisely to the wavelengths the sun puts out most of. The sun puts out a little bit of infrared light and an even tinier amount of radio waves. It also puts out a little bit of ultraviolet light and an even tinier amount of X-rays. But our eyes are simply not sensitive to them because the most efficient thing for our sensors would be to be where most of the radiation is, and that's in the visible light part of the spectrum. There are stars in the universe that emit most of their energy in the X-ray part of the spectrum. That would have been a sensible place to put the planet on which Superman grew up, for example, because then naturally Superman would have X-ray vision. Again, evolution having tuned his eyes to be sensitive to the bulk of the radiation that his parent star puts out. He wouldn't have been born on an asteroid orbiting our sun. The sun radiates at the rate of 400 trillion watts. That's a lot of light bulbs. The energy leaving the star would cool it off, because energy going away means something gets cooler. The atoms give up energy, they slow down, unless this temperature were maintained somehow by some other process. And now we're nearing the end of our definition. A plasma, gravitationally bound, supported by thermal pressure and hydrostatic equilibrium, and emitting blackbody radiation, powered by nuclear fusion. It must be powered by something if it's emitting all that energy. Nuclear fusion is the source of energy that keeps stars shining and maintains their hydrostatic equilibrium. Note, it's not chemistry. The connection of atoms to each other, when electrons are shared between them in a molecule, gives off energies measured in electron volts. In a star, first of all, there are no atoms, the electrons and protons are divorced, but the reactions occur between the protons at scales 10,000 times smaller than the electron orbits the atom, with energies millions of times greater, such that each reaction gives off millions of electron volts, not just electron volts. This is Lord Kelvin's unknown process in the storehouse of creation. Nuclear reactions, which provide so much more energy they can keep the sun shining for many billions of years. Fusion is a process we haven't encountered yet, by which atomic nuclei actually stick together and make new nuclei. Not a simple transformation as in radioactive decay where one or two particles flies out of the nucleus, but the construction of a new nucleus by the fusing together of the nuclear particles, protons and neutrons. Recall that the strong force overcomes the electrostatic repulsion that two positively charged particles would feel once you get to small enough distances. Out here, these two positive particles will sense each other and fly apart because electric repulsion is strong. But if you get them close enough, into a distance of 10 to the minus 14 meters, the realm of the strong force overwhelms the electromagnetic force and forces the particles to stick together. If protons and neutrons can be brought close enough, then they snap together, giving off an enormous amount of energy and creating a new isotope or a new element. Since the nuclear force is so powerful, the energy released is huge, from 1 to 10 million times that of electron-proton interactions that occur in chemistry. The typical nuclear reaction emits several million electron volts for each nucleon involved. Recall from lecture 5, the nuclear stability depends on the ratio of protons to neutrons in the nucleus. Thus, some combinations are more stable than others. And the more stable they are, the more tightly they are bound, the more energy they give off when they're formed. It turns out the most stable arrangement possible is the 26 protons and 30 neutrons which make up an iron nucleus, iron 56. Now again, this is not to be confused with chemical stability, as for example in the noble gases, which don't combine with anything because their electrons orbits are perfectly happy. This is nuclear binding energy, the nuclear particles down on this tiny scale of the nucleus, where the nuclear strong force is the dominant entity, and in which we must arrange protons and neutrons in just such a way that that strong force maximizes stability. Each different isotope of each different element has a particular binding energy. And putting these all on one graph gives us what we call the nuclear binding energy curve, the stability of nuclei. On one axis, the y-axis, we plot the binding energy per nucleon. The amount of energy I get if I stick all those protons and neutrons together. Hydrogen, of course, is 0 because hydrogen has one proton and nothing to bind to, so clearly there's no binding energy. Helium is pretty far down on the curve, several million electron volts for each helium nucleon bound together in a helium nucleus. 2 protons and 2 neutrons bound together, 4 particles, each of them giving off several million electron volts when they snap into place to make a helium nucleus. And so on, down through the light elements in the periodic table, all the way up to iron, where iron, with 56 nuclear particles, represents the ultimate in a stable nucleus. As we add more particles, more protons and more neutrons, to make all the other 66 elements beyond iron, we actually are making slightly less stable nuclei. This is one reason why when we get all the way to the end of the process, out near uranium, none of the isotopes are stable. They are all falling apart due to radioactive decay. Nonetheless, in creating these elements, energy is given off because each time I snap another proton or neutron into place, I get energy. The process that most stars use to shine is the simplest one of all, combining 4 hydrogen nuclei together to make helium. This is a 3-step process, and it's the reaction that powers all stars for the majority, but not all, of their lifetimes. We start off in the center of the sun with 2 protons. 2 hydrogen nuclei, they're simply protons. Now again, when they try to come together, they feel the repulsion of their 2 positive charges and tend to fly apart again. The center of the sun is enormously dense, and at a temperature of 15 million degrees, the particles are moving incredibly rapidly. And so there are millions of collisions per second between one proton and another. But in almost none of these, that is, only once in 10 billion years on average, with 10 million collisions per second going on, so it's enormously improbable, did these particles actually get close enough that they can snap together and stick. Now, once in 10 billion years, you'd think it would never happen, but there are 10 to the 57 protons inside the sun. So on each one has a really low probability of this happening. Altogether, it happens a lot every second. 2 protons coming together to make what? Well, proton plus proton would make a positive charge of 2, and would that be stable? No. We make deuterium. In the process, in the violent collision and the snapping together through the nuclear force, one of the protons is turned into a neutron. And we get deuterium, the heavy form of hydrogen, a nucleus with 1 proton and 1 neutron. That, of course, means we have to balance the charge. We started out with 2 positive charges, we end up with 1. What happened to the other one? The other one goes off in a classic beta decay with an anti-electron, a positively charged electron, flying away along with its ever-present accompanying neutrino. So, hydrogen plus hydrogen come together to make deuterium plus a positron, which goes off and annihilates with some electron somewhere, and a neutrino, which streams directly out of the sun because it interacts so poorly with other particles. Now we've got a deuterium nucleus. What happens to it? Well, deuterium, it turns out, is highly reactive. So as soon as it finds another proton, which will be almost instantaneously because the collisions are so frequent, it gobbles that up and they snap together. Now what have we got? A proton plus a neutron in the deuterium nucleus plus another proton added means 2 positive charges, 3 nuclear particles. We get the light form of helium, helium-3. So helium with 2 protons and 1 neutron, an atomic weight of 3. And in that process, again, the snapping together gives off energy, so gamma rays go flying off through the sun, the ultimate source of the light and heat we get from its surface. Now we've got a helium-3 nucleus. What happens to it? Well, it wanders around in the sun until it finally finds another helium-3 nucleus, which sticks together. Now we've got 6 particles, but what are we left with? Well, that turns out to be unstable. 2 of the protons go flying away, And we end up with the ultimate product of this fusion reaction, helium-4, 2 protons and 2 neutrons, an alpha particle, with 2 other protons re-ejected back into the sun to join the game again. Plus, as always, when nuclear particles stick, we get more energy pouring out of the sun. Why should we believe this picture? I'm telling you about a place that's 15 million degrees, with particles colliding millions of times a second, only sticking once every 10 billion years, yet nonetheless coming together and producing a new kind of element, helium, out of hydrogen in a 3-step process. We can't possibly see what's going on in the center of this star. But we can't see it with visible light. We can't even see the gamma rays that are produced. But we can see what's going on with one of the byproducts of these processes, and that is the neutrinos. Neutrinos, you recall, only interact through the weak nuclear interaction, and that interaction is weak indeed. Neutrinos can pass right through the sun, just as though it weren't there at all, through the intervening 100 million miles of space between us and the sun, and be captured at Earth. But it's the capturing them that's the problem, because neutrinos pass right through the Earth as well. Nonetheless, undaunted by this difficulty, in the 1960s, some scientists built a detector in order to try to catch solar neutrinos to see what was going on in the center of the sun. Well, it turns out it's hard. With a tank containing several 100,000 gallons of cleaning fluid, carbon tetrachloride, once every month or so, a few of the chlorine atoms would get turned into argon atoms. Argon nuclei that were in fact radioactive and could be detected through their radioactive decay. Year after year, decade after decade, Ray Davis filled his tank of chlorine deep in a gold mine in the Dakotas, and once a month cleaned it out looking for this tiny number of argon atoms transformed by solar neutrinos. Remarkably, he found them. But he didn't find enough. He only found a third as many neutrinos as he expected to see. This caused great consternation in the astronomical community because we thought we'd figured out the stars. We thought we could predict to a few percent how many neutrinos should be coming out simply by observing how much energy was coming off the surface and knowing how much energy each reaction in its core must produce. And yet we were off by a factor of 3. This was an astounding result, and for decades caused a vigorous debate between astronomers and physicists. The astronomers, on the one hand, convinced their models were right, said there must be something wrong with the physics of neutrinos. The physicists, with their typical arrogance, said, we understand neutrinos, there's clearly something wrong with the technical details of your messy models that attempt to understand stars. Well, I wouldn't be telling you this story as an astronomer if we hadn't won in the end. It turned out, less than a decade ago, that the problem is with the neutrinos. As you recall from the beginning lectures, there are 3 different kinds of neutrinos corresponding to each of the different generations of leptons or light particles: the electron neutrino, the muon neutrino, and the tau neutrino. It turns out, contrary to the expectations of the standard model, that neutrinos can spontaneously morph from one of these kinds to another. An electron neutrino can become a muon neutrino can become a tau neutrino, and vice versa. What the problem was in Davis's experiment is that the neutrinos on their way from the sun were spontaneously transforming themselves from the type of electron neutrinos that his detector was designed to detect into the other 2 types, muon neutrinos and tau neutrinos. And so the factor of 3 that we were off was precisely right, because a third of them were the kind he was looking for, and the 2/3 were the other 2 kinds. Just perfect. This has now been confirmed by observations that can detect the other 2 kinds of neutrinos, and thus we are quite confident that the models we have built to understand the stars and the elements they create are correct. To make heavier elements, it's even harder, because the electric repulsion you have to overcome becomes greater. The repulsion is proportional to the product of the charges on each of the 2 nuclei. So to stick 2 helium nuclei together with 2+ charges here and 2+ charges here is 4 times harder than joining 2 hydrogen nuclei together. Furthermore, joining 2 helium-4 nuclei together in the violence of the collision, produces boron-8, an isotope which has 5 protons and only 3 neutrons, and therefore is off the nuclear stability line and therefore unstable. In fact, it's so unstable, it falls apart in less than 10 to the minus 16 seconds, which creates a bottleneck in the fusion process, because we can go from hydrogen to deuterium, deuterium to light helium to heavy helium, but when we try to make the next step and fuse helium together, we're stuck. What happens is that the core of the star readjusts such that the helium is in such close proximity that 3 heliums can suddenly stick together, the so-called triple alpha reaction, which brings 3 heliums together to make carbon. 2 nucleons and 2 protons and 2 neutrons plus 2 protons and 2 neutrons plus 2 protons and 2 neutrons makes 6 protons and 6 neutrons, or the highly stable nucleus of carbon. This reaction is the source of most of the carbon in the universe. And this is the reaction that powers the stars after they exhaust their hydrogen fuel. It requires much higher temperatures and densities, however, and this requires a readjustment in the star's equilibrium. In the case of our sun, this readjustment will be fatal for life on Earth, because shortly thereafter, the sun will swell up and the Earth will be orbiting through its atmosphere, a most unpleasant experience. Shortly after that, the sun will run out of its helium fuel and it will also die. More massive stars, however, have an interesting story. They go through multiple cycles of element production, making ever more oxygen and carbon and magnesium and sulfur and iron and all the other elements necessary for life. So, now you know what a star is: a plasma gravitationally bound supported by thermal pressure and hydrostatic equilibrium, usually emitting black-body radiation and powered by nuclear fusion. Does it make them any less romantic to know how they work? I, for one, don't think so. They're not just pinpricks in a velvet cloth letting the supernal light shine through. They're element factories, taking boring hydrogen and helium nuclei and constructing the elements of which our variegated world is made. To complete our atomic history, however, we must first make sure that stars produce the various elements that we find in their observed relative abundances. Oxygen there's lots of, platinum is rare. And then we must arrange for a method by which these newly created elements are distributed to interstellar space, ready to be incorporated into new generations of stars and planets. These are the stories we weave together next time in recounting what we know of the lives of the stars.